All right. Hey, thank you, Jim. Uh, and thank you for the introduction. I think Jim already introduced myself. My name is Amit Nene, and I play like a dual role in Michelangelo platform team. I've been doubling as the architect of the Michelangelo feature store for the last few years, and also running the features and embeddings team within the platform. So today's talk is about the Palette feature store and how it has been helping the entire ML lifecycle across various stages of the ML lifecycle at Uber. So to begin with, um, let's talk a little bit about the history of the feature store. We coined the feature store, as Jim mentioned, back in 2016, and that's when we actually started work on the feature store. We knew that building new features was one of the most time-consuming parts of the ML lifecycle. So we started with a vision of creating a crowdsourced as well as a curated repository of shared features. To a great extent, that continues to be our team's goal. Over time, the feature store took shape as a dual data store system that would manage features for training and serving for the user without having them build ad hoc data pipelines or worry about online offline consistency. Uh, then over time, we built convenience support in the feature store to author feature pipelines using the most common technologies available at Uber, and shared about our work in the well-known blog that Jim talked about back in 2017. We then started onboarding most of the mission critical use cases at Uber and had to really focus our energy on scaling the real time serving stack. Then, in during the pandemic in 2020, a surprising thing happened. While most of our ride sharing business was down, there was an explosive growth in our Eats business, Uber Eats business, requiring us to take the online serving stack to yet another level, to scale to serving millions of queries per second at very low latencies and with a very limited hardware budget. So that was a very challenging time. But having tamed the whole reliability and scalability problem over most of 2020 and 2021, it has allowed us to focus on many new initiatives, such as building an ecosystem around the store to support functionalities such as quality, automatic feature selection, feature monitoring, that I'll be talking about shortly. More recently, we have been also building brand new feature store APIs and metadata to support end-to-end data lineage in the system and support better modularity and extensibility. We are also making embeddings the first-class citizens of not just the feature store, but also Michelangelo, which is currently work in progress. Um, so with that, uh, to really appreciate the role that the feature store plays in an end-to-end model development lifecycle, it'll be helpful to walk through a typical user journey. So oftentimes we can have a ML engineer or a data scientist who may want to create features such as number of trips taken over the last 10 days, number of orders from a particular restaurant, average rating of a user. First thing that they want to do, they know that building features from scratch is one of the most time-consuming tasks. So often the starting point is looking for existing features, and that is what we call feature discovery, which is the first phase. And of course, you may not always find the features that you're looking for, and in many cases, you have to build new features or embeddings from scratch from the upstream data, which is what we call the feature extraction phase, and the feature store offers out-of-the-box support for that. Once the feature pipelines are built, it's time for model training. And what the feature store offers here is what we call as the feature preparation stage, which is essentially generating the training data from all the underlying labels and joining them against the feature tables. And the feature store supports this and at a very large scale. And once a model is trained, it is ready to be deployed in production. It's evaluated and then deployed in production, which in Uber is typically done in real-time environment. So the feature store plays a huge role here because it needs to support a very high throughput, like I said earlier, millions of queries per second, and often because of the inferencing is used in real-time application, the latencies are often the P99 latencies often are sub 100 milliseconds. And having deployed a model in production, we need to continually monitor the model. And monitoring a model is not just about monitoring the model score, but actively monitoring the feature and a drift in the feature distribution, for example, or a drift of the feature distribution relative to the offline training data. And finally, features over time always get revised. Features get shared across multiple models. Features are deprecated, and a feature store supports management of its life cycle. So let's go a little deeper into each of these phases to see the feature store in action. The easiest way to look for features in the Palette feature store is obviously to go to the Git repository of feature definitions, and it's organized into like three layers. The very first top layer is the entity layer, which is the primary entities associated with the features. These are things like heaters, drivers, uh, uh, scripts, and so on and so forth. You may also have the next level, which is a feature group, which you can think of as the logical table of individual features. You go looking for features that sound like you may be interested in. You deep dive one level, you go to the feature level, which is essentially a logical column within a feature group. There is also metadata associated with the feature that you may want to look at when you're choosing a feature, such as the keys associated for lookup, the feature extraction ETL, the online dispersal information. Uh, Another common way to search for feature is to use a keyword-based search rather than going through the Git repository. In this particular screenshot, you can see ML features at the top here. I typed the keyword ether and a 58 results, 58 features popped up here. So I can then go into the individual feature definitions and see if it is indeed the feature I'm looking for. Oftentimes, it's hard to tell whether a feature is indeed what you want by just looking at the feature definition. And you really want to understand what the upstream data pipelines are that are feeding data into it. To make it easier to browse through the lineage of pipelines, we've integrated with Uber's lineage system. In this screenshot, you see a typical flow of how a feature pipeline, uh, how upstream data turns into a feature pipeline. On the left-hand side here, on the top, you have your typical sort of business tables or warehouse tables, dim pack tables. In the middle layer, you have typically staging layers, which join the above data, the upstream data, to perform pre-materialized aggregations over intervals of time. And on the right-hand side, you have the feature store tables, which are not only extracting features, but generating point-in-time snapshots that will then be used later for training as well as dispersed into the online store. Now, the whole process of manual discovery may get tedious, and in some cases, it may not be obvious if a feature is suitable for model unless you throw all the features at the model and try to train it. To solve this problem, for our advanced users, what we have done is we have supported automated feature search through Michelangelo's AutoML tool. So the way this works is an ML user can bring an existing model, and the AutoML tool will inspect its labels, the features, the keys, and go looking for feature store features that are relevant to our target labels. What it ends up with is recommendations of new features that then the modeler can add to the existing model. So this very much reminds me of what Jim mentioned earlier about data-centric AI. this is one technique where you can sort of the AutoML tool goes looking for additional signals from the feature store to enhance the performance of your model. So on to feature extraction. So of course, like I said earlier, if you are unable to discover features, it's time to build new features. And batch computed features are one of the most common ways of building features at Uber. And specifically using batch and some sort of SQL, specifically either Spark SQL or HiveQuery at Uber. So the way the feature store simplifies this, the productionization of feature pipelines, is by allowing a self-service feature authoring interface. So a user comes and just enters all the definitions of the HQL file, the feature definitions and types, and the online configuration. Once the data is just checked in, uh, the feature store will automatically generate all the pipelines. It will start generating the point in time feature snapshot, ingest it into the offline store. It will auto generate the dispersal pipeline, continuously take new data as it comes and copy it to the online store. So the online store will always contain the latest snapshot of the feature, whereas the offline store will contain historic data for the purpose of serving, for the purpose of training and offline evaluation. So one thing to note is that the automation here is one of the key accelerators of the model productionization process. In addition, the self-service interface greatly accelerates model development velocity. Because of this, given any week, we see dozens of commits from our users. Moving on to real-time features, a model may need real-time features often. These are features whose values need to be captured at a smaller grain of time. Whereas batch features are computed daily, the grain of time here is often seconds or minutes. Now, building production pipelines for near real-time feature extraction is a slightly more complex process. Not only do you have to productionize the real-time pipeline to ingest data into the online store at the bottom here, but also generate a pipeline to log the data from real time to the offline store so you have enough data for training. And optionally, you need to build a third pipeline at the top here to bootstrap the computation. Essentially, this involves back computing the data against historical events to produce the features for the first time you're training your model. To make things work, online and offline pipelines often use different compute technologies. So ensuring that the data is semantically consistent online and offline is a pretty challenging problem to solve. Second, you may not always be able to express the complex processing that you can more easily do with batch processing. So that is one sort of downside of using real-time features. Now, one thing to understand is the complexity of the real-time features ecosystem can make feature iteration an extremely cumbersome process. Each time you go through this process and you find that this is not a feature that you want to use, and you pick a new feature, you have to go through this process all over again. So there are two key things that have allowed us to cut down this complexity and dramatically reduce the model's time to launch. The first thing is automation. Automating these various pipelines, ensuring that the online and offline data is consistent. That is the first step. B, choosing the right infrastructure to ensure that there is online and offline consistency. In our case, we chose Athena X, which is the homegrown streaming SQL solution available at Uber, and we worked with the data team to set up this bootstrap pipeline, which ensures online and offline consistency. Now, feature onboarding is the same as batch features. User goes and checks in their code here to the feature spec Git repository. Once the code is committed, the pipelines are kicked off, and the data starts ingesting into the offline and online stores. Moving on to model training, we have our production pipelines ready, and it's time to start training the model. The first thing we do before kicking off the model training is to make sure that the feature store data is clean and does not contain errors. The one detail I left out in my previous slide is that right after we onboard features, we kick off these data quality pipelines that then produce test results and record it in a data store for use later during training. We also automatically page the respective on-calls uh, so that the data is repaired right away versus waiting to do so at training time. On the right-hand side of this picture, you can see the screenshot. This is a screenshot from our, like at the time we kick off the training job. We kind of run 5 tests in this case, and you can see there are tests around duplicates, like there are features with duplicate keys, which is something we don't want. We have things like missing partitions, null features, and so on and so forth. So the key thing to the takeaway from here is that taking care of such low-hanging fruit can save ML developers hours or days of time otherwise spent debugging and resolving issues discovered during training failures. Having trained the model, uh, having trained the model, uh, it is having actually validated the data of the model. It's time to actually kick off the training. The feature store plays a big role in the first step of training, which is feature preparation. What this involves is joining all the training data containing the labels against the various feature tables that the model is using, and spanning several months of data using what is known as point-in-time joins. What that means is that the labels will be joined against the values of features observed exactly at the time of the label. Now, we've seen in some cases, the model, this processor, the feature join can involve joining like hundreds of terabytes of data, and this can make the process very inefficient. So it is critical to accelerate, to make this, to optimize the system to accelerate the velocity of model training. And in our experience, the key to cutting down this cost is to optimize the underlying shuffle operation, which is what Spark uses to implement joins. We've also introduced a special on-storage data layout called Delta Store to incrementally compute point-in-time snapshots to reduce the amount of data joined during feature preparation. In addition, Michelangelo provides a DSL uh, for performing lightweight transformations or model-specific feature transformations. This provides the users the flexibility of quickly iterating over model features. Say you have a feature which is seconds, you want to turn it into milliseconds, you can do quick transformation to the DSL, and this avoids having to backfill months worth of data if you had done this at the ETL or the data layer before ingesting into the feature store. So again, this is one of those things that helps boost developer velocity. Moving on. Now, once the model is offline evaluated, I should have mentioned that the offline evaluation uses the same exact structure. We use the offline testing data or validation data, join, offline joins, and evaluate the performance. And to see it, once it's like deemed optimal, it's time to actually deploy it in production. And production, in our case, majority of the times is a real-time system. So you can see from this screenshot, the architecture is very like semantically identical to the offline system. Instead of the offline store, you have the online store and a caching system on Redis, the online store. Instead of the labels, we have the context, that is the keys being passed from the upstream service. The feature assembly is not a full table join, but just a few rows of features joined together using the keys passed in. And then DSL is applied on those joined features. DSL works in a way where the code is designed to execute symmetrically in online and offline environments. The exact same transformations are performed even at inferencing time. And the final feature vector is passed on to the inferencing system. Now, one of the key things that at Uber at least, we end up serving millions of queries per second from the feature store. So planning for capacity is a very crucial step in being able to launch the model in a timely. The requesting the use of like inordinate amount of hardware to support this throughput may end up delaying the launch because oftentimes the hardware is not available. So towards that end, we follow a process that takes the model's access patterns, features used, size of the table, and apply various optimizations and plan for various features for optimization to come up with the best estimate of the sample and capacity for online serving. Now, our eventual goal is to fully automate the capacity estimation process and also automatically provision the underlying storage. One other thing I'll mention is that has helped us to accelerate the whole deployment process is the use of shadow testing environment. If you're able to clone a percentage of the production traffic and run it against the inference server and the store to test the system at a reasonably high scale without affecting or causing outages in the upstream business flows. Now, successful testing in a shadow environment provides us with the confidence of then graduating this model to the actual environment. Now, let's say the model is now deployed in production. It's not done. We are not done yet because we need to continuously monitor the performance of the model to be sure that it is not drifting away. And one of the key things we need to monitor is not just the prediction score, but also the feature store features, and specifically whether the distribution of the features has drifted away from a baseline. And the baseline that we use is often constructed from a historical sort of inferencing data or a model training baseline. And we try to detect this drift between the online distribution and the baseline distribution in near real time. So within a few minutes, our system will tell you that your features are drifting away. So just as an example here, you can see for this particular feature, this is an actual screenshot from an actual production feature. You can see that the training baseline and the online baseline on the left, you can tell that the feature has is way off the baseline. The Palette feature store or two kind of directly implements its own monitoring, but it does so in an offline manner. That monitoring is mainly done to sort of ensure that the data has a good distribution, predictable distribution at training time, but also before dispersing data to the offline store. So the takeaway here is that the two systems really complement each other, the real-time system and the offline system, in a way that to ensure that the features are detected in a timely manner and potentially avoiding several days of outages. Finally, I'll talk a little bit about the evolution of features.
We'll have to kind of go through it a bit quick. We're kind of run out of time.
I'm wrapping up.
Great.
Yeah. So finally, we'll talk about a bit about the evolution of features. We observe that over time, features get organically adopted across multiple feature models and maybe revised to newer versions. So it is really important not just to maintain a lineage with the upstream data pipelines that you saw earlier, but also to the models using it. So that when a feature is being removed, we go through this two-step process where we first deprecate, soft block the training, and then eventually when all the feature references to the models are removed, we can actually safely remove the feature. Really, very quickly, just to sum up how the feature store plays a role in accelerating end-to-end ML, we saw how feature support in the feature store can accelerate the search for features, also specifically through automatic feature selection. We saw how automation plays a big role in speeding feature extraction. We saw how feature federation and scalability in join is critical to speed up training. We saw how a good process for capacity planning can speed up model deployment and shadow testing. We saw how near real-time feature monitoring via the prediction logs and offline feature monitoring work together to prevent potential outages. And finally, we saw how a feature store can help you manage the life cycle of features, evolving features. So thank you. I think I'm at time. So most likely I'm going to take the question.
Yeah, thanks a million, Amit. That's been fantastic.